Hi guys, so we've got ourselves another question here. So this question says that it is possible that the Newtonian theory of gravitation may need to be modified at short range. Suppose that the potential energy between two masses m and m prime is given by this guy. So this is the potential energy given by minus gm m prime divided by r 1 minus a exponential minus r over lambda. Question then says for short distances r much more less than lambda, calculate the force between m and m prime. So you don't need to bother yourself about the notation, but you know that Newton's theory of gravitation just tells you that whenever we have two masses, then there is a force of attraction, just a force of attraction, no repulsion this time around. A force of attraction between the two masses, and this force has a magnitude, which is given by this gm1 m2 divided by r squared. So this is Newton's law of gravitational force in the scalar form, but it can also be in the vector form. But we don't need to concern ourselves with the theory. So the question says we should reduce this, or we should find the force rather, provided that r is much more less than lambda. That means r is very small compared to this lambda. Okay, like I said, we don't need to bother ourselves with the notation. So the question you need to ask yourself is, how do you obtain a force from given that you are given a potential function? So you need to recall that if you are given a potential, then the force, which is a vector quantity, the force is minus the derivative of the potential. So the derivative of the potential is going to be minus the v of, in this case, the potential depends on r, not x. So r can be maybe x, y, z, can be 3 dimension divided by the r. So what we're just saying is that for we to, now this is going to be partial. Let me change this symbol to partial. I will explain the reason I'm changing it to partial. Partial means whenever you see the d to be called this way, then it is partial derivative. Why is that? We're having different variables here, not just r. We have a, we have lambda, we have m prime, g. Yeah, so we have quite a lot of variables here. I think about 4 or 5. So because of that, you are meant to use partial derivative. It doesn't matter what you might know. You don't need to know partial derivative. Just need to know the simple rule of differentiation, and you're good to go. Okay, substituting this function inside this. So this is going to be minus the r of everything here. This is v of r is everything here. So that's going to be minus gm m prime divided by r 1 minus a exponential minus r over lambda. We have this. Let's close this guy. Okay, so the minus can cancel, minus and minus is plus, so definitely we can have this to be dr of gm m prime divided by r 1 minus a exponential minus r over lambda. Okay, so we can factorize gm m prime. Since it is a constant, it doesn't depend on r, and that's the reason for this called d, because we are taking orders as constants, but we're differentiating with respect to r. So let's factorize this out. So this is going to be g m prime d dr of, this is now going to be 1 over r, open bracket 1 minus a exponential minus r over lambda, close this bracket. Okay, so let me get rid of this. Okay, so let's expand what is in this bracket here. So this is going to be g m prime d dr of 1 over r minus a over r exponential minus r over lambda. This is what we have here. So this is going to, we're going to differentiate this function one after the other. So this is going to be g m prime d dr of 1 over r minus ddr of a over r exponential minus r over lambda. So this is what we have. Just use this to put this off. So at the end of the day, we're going to have gm m prime open brackets. Now this is the same thing as the dr of r to the minus 1. And this here is we're going to need to apply product rule to this guy here, because we have a over r. We have one function which depends on r, another function which also depends on r, placed side by side. So this is product of two functions. So this is going to be minus. So product of two functions, to apply product rule, you leave the first guy here, that's a over r. You differentiate the second guy, ddr of a exponential ddr of exponential minus r over lambda, then plus, you leave the second guy, exponential minus r over lambda, you differentiate the first guy, dr of a over r. So we're just applying product rule. Okay, so this guy gives us g m m prime. If you differentiate this by power rule of differentiation, we're going to have minus 1, and just minus 1r. And that's just, I want to assume we all know this. Drop down the power, subtract 1 from the power, that will be minus 1 over r squared. If you differentiate this guy, okay, let me show the workings. So this is minus r, minus 1, minus 1, minus this. If you differentiate this here, you just use, if you differentiate exponential function here, so this is going to be a over r dot, now this is going to be minus 1 over lambda exponential minus r over lambda plus, if you differentiate this guy here, this is going to be, let's say we still have exponential minus r over lambda dot, this is going to be minus a over r squared. I've jumped a step here, but still the same thing as just differentiating 1 over r. If you differentiate 1 over r, is 1 over r squared minus 1 over r squared. So multiply by a, that's minus a over r squared. So this here is going to be, let me just rub this off. And as we've done this, this is just minus 1 over r squared. Okay, so we're going to have this to be, let's open this bracket up, and this is going to be minus 1 over r squared minus, before we open this up, let's quickly simplify this guy. This is going to be minus a over r lambda exponential minus r over lambda plus, let's say minus, plus times minus is minus, that's minus a exponential minus r over lambda divided by r squared. Okay, let's factorize minus 1 over r squared out. So if you factorize minus 1 over r squared out, or possibly let me still simplify this. This is going to be g m prime minus 1 over r squared plus, minus is plus, a over r lambda exponential minus r over lambda, and plus a over r squared exponential minus r over lambda. So just use this minus to put this up. And let's factorize 1 over r squared out so that we can have the original function back. So this is going to be, I'm factorizing minus 1 over r squared out. So that's going to be minus g m prime divided by r squared. So I'm going to have here to be 1. So I've already factorized minus 1 over r squared out. So definitely I expect this numerator to have, if I factorize r squared out, come in. So this will be minus, that should be a over r lambda, or let's say that should be ar over lambda. If I factorize 1 over r squared out, and if I still bring the 1 over r squared in back, 1 over r squared times r is into 1 over r, so the r will still be there. I want to assume you know this, what I've done there. So this is going to be exponential minus r over lambda. Then we have minus a exponential minus r over lambda. So this is what we have. Okay, so with this, you can apply the condition given earlier. The condition is, he said, given that r is much more less than lambda, and r is very small. So this implies that r over lambda is much more less than 1 if I divide both sides by lambda. Okay, so that means this is very small compared to 1. So it's like approximately 0. So we can neglect it. So this means that the r over lambda here, at this region here, sorry, the r over lambda here is actually approximately 0. Also, the r over lambda here is 0. The r over lambda here is 0. So therefore, our force, our F of r, which is the force, is given by minus gm m prime divided by r squared, open brackets, 1 minus a times 0 dot exponential 0 or minus 0, there's nothing like minus 0. 0 is neutral, so minus a exponential 0. And if you simplify this guy further, we're going to have that therefore f of r is actually going to be minus gm m prime divided by r, open bracket, 1 minus, this is already 0, this is 1. 1 times a is a, m raised by 0, exponential 0 is 1, so 1 times a is a, so 1 minus a. So this is our, oh, okay, there's a square. So this is our potential, sorry, our force obtained from the potential function. So basically, if I have to find the force given the potential, it differentiates the potential energy to get the force. And if I have to get the potential energy back, you integrate the force. So it's just the opposite.